Hello, I'm Seonung. Today I will review a paper from the ICLR 2026 conference. The title of the paper is CE-Nav, Flow-Guided Reinforcement in Refinement for Cross-Embodiment Local Navigation. This paper addresses an important problem in vehicle navigation. It presents a method to create a single navigation policy that works on many different types of vehicles. Let us begin. Here is the outline for today's presentation. First, in the instruction, I will explain the motivation for this research. I will discuss the limitations of existing methods and share the main contribution of this paper. Next, I will briefly review related works. After that, I will explain the method in two parts, Stage 1 for imitation learning and Stage 2 for reinforcement learning. Finally, I will show the experimental research and conclude. Let us start with the motivation. Please look at the images on the screen. There are many platforms such as Magic Dog, Spot, H1, and Hummingbird. The authors refer to these different physical shapes as diverse morphologies because each platform has different physical dynamics. Creating one universal navigation policy for all of them is highly challenging. The goal of this paper is to build a cross-embodiment framework. The authors aim to design a system that achieves high performance on any vehicle while keeping the time and cost of adaptation to a minimum. To understand the difficulty of this task, let us examine the limitations of existing approaches. There are two main methods, and both have structural limitations. First is the end-to-end policy. This method maps the sensor observations directly to the low-level motor commands. It mixes the route planning and the vehicle's physical dynamics too closely. When third policy is applied to a new vehicle, it generally fails. Second is the hierarchical method. This method separates the path planning from the motor control. However, the high-level planner assumes the vehicle moves perfectly. In reality, vehicles have tracking errors, and this method cannot compensate for those physical errors. To resolve these issues, researchers often use hierarchical velocity planning. This approach improves upon previous methods, but it still has two major limitations. The first is embodiment-specific bias. The model relies on expensive data collected from one specific vehicle, making it difficult to generalize to other vehicles. The second is the disastrous averaging problem. In deterministic models, the system must output exactly one action. For example, at a T-junction, a vehicle can safely turn left or turn right. Deterministic models attempt to methodically average these two valid choices. As a result, the vehicle moves straight and hits the obstacles. This is an artificial failure. To address these limitations, the author introduced CE-Nav. CE-Nav has three main contributions. First, the authors propose a two-stage framework, limitation learning followed by reinforcement learning. This framework completely separates universal geometric planning from vehicle-specific dynamic adaptation. Second, they introduce Verflow. Verflow learns the full distribution of safe actions rather than a single average path. This effectively solves the digitalized average problem. Third, this training strategy still achieves a high performance without using costly vehicle-specific data. It also the policy to adapt to new vehicles quickly and stably. Now let us review related works regarding navigation modeling. Classical local planners like DWA are effectively for local obstacle avoidance. However, their parameter must be adjusted manually, and they often vary in environments with complex obstacle layouts. The learning approaches also have limitations. End-to-end methods require a massive amount of embodiment randomization data to function properly. Hierarchical methods frequently ignore the tracking errors of the specific low-level controller, leading to suboptimal navigation performance. Next, I will discuss multimodality, which refers to handling multiple valid decisions. As mentioned earlier, deterministic models output only one answer, meaning they fail when their decision is ambiguity. Recently, general models like diffusion and flow models have shown promising research because they can capture multiple valid actions. However, previous studies mostly utilizes them only for pure limitation learning. CE-Nav is different. The authors integrated a flow-based model to capture multiple expert actions in stage 1 and then utilizes those actions as a guide for online reinforcement learning in stage 2. Let us move on to the method. Please look at the diagram. I will first explain stage 1, located on the left side. Stage 1 trains the general expert. This policy is embodiment agnostic, meaning it does not depend on specific vehicle. It only learns universal planning principles, such as avoiding obstacles based purely on geometric data. Here is the step-by-step process. First, regarding the data collision process, the authors trained the general expert offline using limitation learning. They did not use real vehicle data. Instead, they used a 2D simulation. In this simulation, the agent is modeled as a simple circular rigid body, which eliminates any bias related to a specific vehicle's shape. The authors used the classical TWA planner to navigate through tens thousands of procedure-generated environments. Crucially, when the planner found multiple safe and big high-scoring actions, the authors explicitly saved all of them. This results in a large dataset of 10 million saved state action pairs. The input for this policy is called the input state. It consists of two components. The first component is a 2D raycast. This is a 144 dimensions vector that measures distance to surrounding obstacles up to a 4-meter range, processed by a CNN. The second component is the robot state. This is a 7-dimensional vector containing the normalized core directional current linear velocity, current angular velocity, and Euclidean distance to the goal. This is processed by an MFP. The authors combine these features to produce a 256-dimensional state embedding. Here is a diagram showing the robot state clearly. It displays the component of the 7-dimensional vector. It includes the normalized core directional in the x, y, and z axis. It includes the distance. Labeled as d, it also included the linear velocity and angular velocity by utilizing this basic geometric information. The policy completely avoids the need for expensive real-world vehicle data. As indicated by the red box on diagram, the 2D raycast and the robot state are processed by the state encoder. The state encoder combines these inputs and outputs a condition. This condition contains the necessary environmental representation and serves as the exact input for the flow model in the next step. The next component is flow, indicated by the red box. Flow receives the condition generated in the previous step. The author utilizes the flow to fundamentally solve the digital averaging problem. flow is a conditional normalizing flow model. It does not output a single deterministic mapping. Instead, it learns the complete conditional probability distribution of the expert actions. It understands that both turning left and turning right are valid actions. The authors choose a flow model over a diffusion model because it can sample from complex distribution in the single propagation. This makes it fast and computationally feasible for real-time control. Regarding the training of Airflow, the author based the design of the little MVP network architecture. It learns to map a single base distribution, which is a standard Gaussian noise called Z, to the complex expert velocity distribution. The loss function is trying to minimize the negative log likelihood of the expert demonstrations. Once trained, inputting random noise jet allows Airflow to transform it into diverse and kinematically sound reference velocities. This accurate geometric plan is the final output of stage 1. Now that the author have prepared this geometric place from stage 1, let us move on to stage 2 see to how they apply this to actual vehicle in the physical world. Now, let us move on to stage 2. In stage 1, the model learned general geometry navigation knowledge. However, that alone is not enough for a real robot because each robot has different dynamics and control errors. So, in stage 2, the authors train a dynamic aware refiner. The key idea is simple. Keep the general expert frozen and learn how to adjust each output for a specific robot. This allows fast adaptation with only a small amount of online interactions. First, let us look at the guided state input. The first part is the same 2D laycast that was also used in stage 1. This is a 134-dimensional LiDAR style scan obtained from 360-degree 2D laycast with a maximum range of 4 meters. In other words, it tells the robot how far nearby obstacles are in every direction. This input is useful because it is simple, geometric, and also robust for sim-to-real transfer. The second part of the input is the robot state. This is a 7-dimensional vector that contains the normalized course direction, current linear velocity, current angular velocity, and the Euclidean distance to the goal. So this part tells the policy where the goal is, how the robot is moving now, and how far it still needs to go. Together, the laycast and the robot state describe both the environment and the robot's current motion status. Next, the model uses a reference velocity. This reference velocity is sampled from Airflow, which was trained in stage 1, so the frozen general expert proposed a geometrically reasonable action first. This is important because the refiner does not start from nothing. Instead, it starts from a strong prior that already knows how to move safely around obstacles. After that, the state embedding from the state encoder is concatenated with the reference velocity. This combined feature is called the guided state. The guided state is then fed into the actor and critic networks, so the actor and critic do not only see the raw observation, they also see the expert's suggestion. Because of this, the refiner's job is not to relearn navigation from scratch but to refine one expert proposal into a better command for the target robot. Now let us look at the action output. The policy predicts the final velocity command. It first outputs a normalized value between 0 and 1. Then this value is linearly converted into the robot's actual velocity range from -1 to 1 after scaling. In short, the network predicts a safe to normalized action first, and then maps it into the valid control range of the robot. This makes the output easy to train while still matching the robot's real command limits. The author said an unsurety guidance loss. This loss is a mean scared error between the refiner output and the scared reference velocity from Airflow. The purpose of this loss is to keep the refiner close to expert sensible proposal, especially in the early phase weeks of training. Because of that, training becomes more stable and the police can learn more efficiently. At the same time, the refiner is still allowed to deviate when needed, so it can adapt to the laboratory dynamics. Besides the guidance laws, the refiner is trained with PPO using several reward terms. The reward includes core progress, sustained progress heading alignment, core complication, and modal smoothness, body state level, obstacle coherence, and collision avoidance. So the reward is not focused on only one thing. It encourages the robot to move toward the goal, but also to move safely, smoothly, and stably. This balance is important because a robot that only chases the goal may move too aggressively and fail in practice. Let us first look at the goal-related works. The first term is goal progress. This term rewards the robot whether it gets closer to the goal at each step. The second term is sustained progress. This term rewards longer than progress toward the goal, and in the paper it is evaluated and checkpoint. The third term is heading alignment. This rewards the robot when each moving direction is aligned with the goal direction. Core complication gives a large sparse reward when the robot successfully reaches the goal. Together, these terms push the robot to move in the right direction and finish the task efficiently. On the slide, the focus is linear motion smoothness. This term penalizes sudden changes in linear velocity, so it encourages smoother forward and sideways motion. Next is yaw motion smoothness. This term penalizes abrupt changes in turning speed, so it encourages smoother rotation. Now let us move to the last group of levers. The first term here is body stability. This term penalizes excessive body tilt to keep the robot physically stable during motion. The next term is obstacle clearance. This term rewards the robot for keeping a safer distance from nearby obstacles. Finally, there is collision avoidance. This term applies a large sparse penalty when the robot collides with an obstacle. Now, let us move on to the experiment. First, I will explain the simulation environment. The authors use a challenging environment called the obstacle forest in Isaac Sim. This environment is defined as a scary area filled with randomly sized and randomly positioned cuboid obstacles. During training, they use 500 obstacles in a 40 by 40 meter area. This setup is intentionally very dense to stress test the robustness of the navigation policy. As shown on the right, the 2D lakeheads visualize how the robot perceives the environment using distant measurements. This allows the model to learn navigation under highly cluttered conditions. Next, I will present the quantitative research from the ablation study. First, the full CE-Nav model achieves the best success rate and SPR across all obstacle densities, while requiring only 6 hours of extra training. This shows a strong balance between performance and efficiency. Second, the GE-only variant collapse and the regression-based variant even performs worse than pure reinforcement learning. This indicates that online refinement is essential, and a poor unimodal teacher can actually harm learning. Third, although variants like diffusion guidance or fixed guidance improve over weaker baselines, they still perform worse than the full model. This demonstrates that both a high-quality multimodal flow teacher and a curriculum-based guidance strategy are critical for the final performance. Finally, let us look at the comparison and generalization research. On the unitary GO2 platform, CE-Nav achieves the best overall performance, outperforming classical methods like TWA, as well as learning-based methods such as BC, TP, and NavRL. At the same time, it reduces the extra training time to only 6 hours compared to 50 hours for NavRL. More importantly, the method generalizes well across different global platforms. Using the same pre-trained general expert, the model adapts to quadrupeds, a biped, and even a quadrotor with only a short RL pace. This research shows that CE-Nav is not only strong in standard benchmarks, but also robust to differences in robot shape dynamics and controller characteristics. To conclude, CNF separates embodiment agnostic geometry reasoning from embodied specific dynamic adaptation. It does this is not by combining a multimodal general expert with a lightweight dynamic software refiner. In other words, the model first learns general navigation knowledge and then quickly adjusts that knowledge to a specific robot. I think this separation is the key idea of the paper. Another important point is the lure of flow and guided reinforcement learning, where flow models diverse expert velocity proposals instead of forcing the police to output only one average action. Then guided reinforcement learning refines this proposal into visible comments for each robot. Because of this design, the method can stay both flexible and stable during adaptation. The experimental research are also strong. CNF outperforms strong baselines, generalizes across quadrupeds or biped and a quadrature, and also transforms successfully to real-world deployment. So the method is not limited to one robot type or one simulator setting. This supports the main claim of cross-embodiment navigation. Overall, this framework removes the need for costly robot-specific real-world data. At the same time, it provides a scalable local navigation module that can be integrated with higher-level planners such as vision language models. So beyond this paper alone, CNF can also be seen as a useful building block for more general robotic systems. Thank you for listening. And if you have any question, I will happy to take any question. Thank you.